Let's just clear up some confusion regarding this tutorial problem. What's important to understand is what Vogler tries to say is that there's a changing linear velocity in his reactor, but he evaluates the rate at a point where the concentration is constant. We have the same concentration for all the rates reported here. So the thing that is changing is a linear velocity if it's a PBR. If it's confusing to you, rather switch this in your mind, this example or this stat, to represent changing RPMs in a CSTR. So we have a low RPM to a high RPM measurement. The concentration in the reactor is the same, and we measure the mass-based rate as we change the temperature. So what this implies is if we change the temperature, we change our Thiele modulus, and if we change our Thiele modulus, we change our effectiveness factor. If we change the RPMs, we change our Kc value, or our external mass-based rate constant. It is also a function of temperature, but much weaker function of temperature than our Thiele modulus, which got the exponential increase in temperature here, and therefore this parameter eta much more sensitive to a change in temperature than Kc. So let's first try to answer this question. In which region, if we need to quantify, can we observe no external mass transfer effects, or where can we say that the bulk phase concentration is equal to the surface concentration? That, of course, is at a point where the stirrer speed does not affect the rate anymore. So if we should analyze this, definitely that happens at the higher stirrer speed runs. So these higher stirrer speed runs over the entire temperature range, both of them follows each other exactly. The rates follow each other exactly regardless of a difference in the stirrer speed. So here I can definitely say that Ca bulk is equal to Ca surface. There's another region where that is true, and it is at the low temperatures for the 400 RPM stirrer speed. Here I can see that about to 362 Kelvin, my rate line follows these two higher stirrer speed rate lines, and then it starts to deviate. So why does that deviation occur? As the temperature increases, there's no significant increase in temperature with Kc. However, my Ki dash increases exponentially. So what happens in this regime where these two lines start to deviate, where this 400 RPM lines start to split off from those other higher stirrer speed lines, is that the Kc can't keep it up anymore. So over here, if I look at my effective rate constant, what is going to happen if I have a first order reaction is that Kcam does not increase. So this resistance to Kcam relative to the resistance to the intrinsic reaction rate becomes much larger, and over here Ca surface becomes much smaller than Ca bulk. The external diffusion can't keep up. At lower temperatures, this value is high enough so that this resistance relative to the resistance to the intrinsic reaction rate becomes negligible. So if we now analyze the same figure and we want to recognize the regions where eta is equal to 1. So we have no internal mass transfer effects. What we must realize is the only parameter in this scenario that affects eta will be temperature. That's the only parameter that's present in the Thiele modulus in this scenario. I don't change my particle diameter, so only thing that can affect eta is the temperature. So when we consider the two rate lines where I have no external diffusion, I can still see that there's a little something weird happening here. I have this exponential increase, I have a little wobble, and I have another exponential increase. If my rate was free from any internal diffusion effects, I know I'm free of external diffusion effects in that regime. If it was also free of any internal diffusion effects, I should expect an exponential increase increase in the rate. Remember, the concentration is the same. Ca surface is now equal to Ca bulk. So I would expect that only my rate constant, K0 times exponent minus to the power of minus E over RT affects the rate. So I have my true activation energy here. However, what I observe is that I have this little kink, and then I have a different exponential increase. So the rate still increases exponentially, but at a lower increase with temperatures, because I observe my apparent activation energy where I go into that internal diffusion limited regime. Once I reach about this point, after I have a little region where I have in between regime between my internal diffusion controlled and my rate controlled regime. So what I can now say is that there is a temperature below which my eta value is equal to 1. And that is true whether I have external diffusion present or not. Eta is equal to 1. So what this implies is that even at this 100 RPM run, over here, eta is equal to 1. So I have no internal diffusion. However, external diffusion affects my rate. For the line where I have the 400 RPM, no internal or external diffusion up till this temperature, and there for this part still no internal diffusion, eta equal to 1. However, the external diffusion resistance start to play a role, and Ca surface is not equal to Ca bulk, even though eta is equal to 1 in that temperature range. So as soon as I go to the higher temperature ranges, so for these two runs where I have the lower RPMs, when I now evaluate this part of my diagram, this regime here, I have external and internal diffusion effects. Ca surface less than Ca bulk, eta less than 1. Same over here, Ca surface less than Ca bulk, eta less than 1. So now that I am aware of the fact that at lower temperatures my eta is 1 and at higher temperatures my eta is less than 1, and I know where I can expect external diffusion effects, I can start answering all kinds of interesting questions about my rate. And one of them, Vogler wants to know what is the effectiveness factor at a specific temperature in this reactor. We need to remind ourselves of the definition of effectiveness factor to answer this. It says that this is what is the rate that is observed in my reactor divided by what is the potential rate if my catalyst was free of internal diffusion effects. Remember, the effectiveness factor refers to internal diffusion effects, so we need to quantify that at a point where we exclude the external diffusion effects. So here we will have to have our actual rate that is on the orange line, and we divide that by a rate. If we extrapolate this higher activation energy, if we extrapolate that line, we can read off what could the rate have been at that temperature if it was free of any internal diffusion effects, and that's the way we can calculate our effectiveness factor. Of course, those who want to have a more quantitative grasp on this problem can take some data from the points where the green line applies and calculate your K0 value and calculate your activation energy, and then you can actually calculate at that high temperature what the rate would be that you expect at that higher temperature if you had no internal diffusion effects. And once you know how to quantify your eta value at any temperature on this figure, it would be easy to expect you, or realistic, not easy, realistic to expect of you to calculate at a certain temperature what is my Kc value, because I know what my rate is, I know I can quantify my effectiveness factor, I know what my intrinsic rate constant is, I can quantify all kinds of things and calculate Kc at any point, calculate eta at any point.